You know, we usually think of our modern information age as this completely ethereal thing, right? Cloud computing, invisible wireless signals just floating through the air. But in this explainer, we're going to see that the foundation of all our cutting edge tech is actually incredibly physical. Honestly, it's built on a rock. So I've got a bit of a riddle for you. What exactly connects ancient Greek ice to the smartphone you're probably holding right now? Sounds kind of crazy, I know, but the answer is actually a primitive, incredibly common mineral that is quite literally pulsing with the invisible power needed to drive modern telecommunications. And that mineral? It's quartz. All right, here's our roadmap for this explainer. We're going to cover the hidden technological hero, the physical and colorful properties of quartz, the power of piezoelectricity, how it shaped modern history, and finally, its role as our invisible industrial backbone. Let's dive right into Section 1, the hidden technological hero. If you were to break down the Earth's lithosphere, that rigid, rocky outer layer of our planet, you'd find that quartz is absolutely everywhere. Mathematically, it's expressed as silicon dioxide, and it makes up a massive 12% of the Earth's lithosphere by mass. That puts it right behind feldspar. Because it's so incredibly resilient to weathering, it's a primary component of the sand on your favorite beach and the sedimentary rocks up in the mountains. I mean, it is the very definition of abundant. Moving right along to Section 2, physical and colorful properties. Before we get into its high-tech superpowers, we've got to appreciate its sheer visual variety. In its purest form, quartz is completely clear, just like glass. But in nature, trace elements can totally transform it. For instance, if tiny amounts of iron get trapped inside the crystal lattice, boom, you get the stunning purple of an amethyst. If the quartz is exposed to natural irradiation down on the Earth, it turns into this dark, smoky quartz. Or if it's packed with microscopic fluid inclusions that got trapped when it was forming, you get the opaque white of milky quartz. But hey, do not let the pretty colors fool you. This is an incredibly tough rock. On the Mohs hardness scale, which is a classic tool for geologists, quartz sits at a really solid 7. To put that into perspective, it can easily scratch a steel file. Plus, quartz doesn't have what geologists call cleavage, and no, that's not a joke. It just means it doesn't naturally break along weak, flat planes. It's super resistant to mechanical stress and can survive intense chemical attacks. Actually, you generally need something as extreme as hydrofluoric acid just to dissolve the stuff. Because pure quartz looks so much like clear glass, ancient philosophers, like the Roman naturalist Pliny the Elder, actually believed it was a form of permanently frozen, supercooled ice found near glaciers. Yep, that is our ancient Greek ice connection. And that belief actually stuck around for a long time, right up until the 17th century. That's when a scientist named Nicholas Steno made a massive structural breakthrough. He realized that no matter the size or shape of a quartz crystal, its long prism faces always meet at a perfect 60-degree angle. This brilliant little observation, it essentially paved the way for modern crystallography. All right, on to Section 3, the power of piezoelectricity. So the secret to quartz's superpower lies in a property called piezoelectricity. The root word here is piozane, which is Greek for to press, and that is absolutely crucial to understanding this mineral. See, certain crystals, when you apply physical pressure or mechanical stress to them, actually generate an electric charge right on their surface. It's literally turning a squeeze into a spark. Think of quartz like a microscopic translator. When you apply mechanical pressure, the actual internal structure of the crystal changes shape, and that shape change, it generates an electric charge. It literally translates the physical language of pressure into the invisible language of electricity. But wait, it gets better, because it amazingly works in reverse. If you zap a quartz crystal with electricity, it physically changes shape or vibrates. This incredible two-way translation is the secret engine running our modern devices. Which leads us straight into Section 4, shaping modern history. Now, it didn't take long for scientists to realize this wasn't just some neat party trick. Back in 1880, the French Curie brothers, Pierre and Jacques, first discovered the piezoelectric effect using materials like quartz and tinfoil. Then, by 1910, Waldemar Voigt published the complex math needed to actually measure and harness this electricity. And then, history really accelerated. During World War I, the intense pressure of warfare led French scientist Paul Langevin to use quartz's piezoelectric properties to invent the first passive sonar device. It was used to locate ocean submarines. By World War II, the demand for sonar and military tech was off the charts, so scientists developed manufactured piezoceramics, like PZT. These had dielectric constants, which is basically their ability to handle electrical energy, up to 100 times greater than natural crystals.
And that brings us to section 5, the invisible industrial backbone. $34.7 billion. That is the staggering projected global market value for piezoelectric devices by the year 2025. I mean, this isn't just some niche scientific field anymore. It's a massive, sprawling global industry. What started as a way to detect submarines has blossomed into an absolutely essential component of modern life.
To really wrap your head around that $34 billion number, you just have to look around you. Because quartz is everywhere. In healthcare, it's the core of the ultrasonic transducers used in ultrasound probes. In your car, it's sitting right there in the fuel injector sensors and even the proximity sensors for your backup camera. Over in heavy industry, quartz sand is used as a flux in metal casting to wash away impurities. And in the petroleum industry, it holds open fractures in bedrock during hydraulic fracturing. In electronics, wow, it's the beating heart that provides the exact perfect frequency for radio transmitters, GPS devices, and computers. And look, we absolutely cannot talk about the information age without talking about fiber optics. I love this quote from the Quartz Corp. They say 1 ton of spruce pine quartz goes into approximately 38,000 kilometers of fiber optic cable. That is just mind-boggling. By taking high-purity quartz, specifically from places like the Spruce Pine Mining District in North Carolina, we can stretch a single ton of this ancient rock into 38,000 kilometers of flexible, transparent strands. And those strands transmit the light signals that power the entire global internet. But here's a really fascinating twist for you. The quartz in your electronics today, it's probably not from the ground at all. Historically, sure, the electronics industry relied on natural quartz mined from places like Brazil. But when World War II completely disrupted those supply chains, human ingenuity had to take over. Today, virtually all the quartz crystals used in the modern electronics industry are synthetic. We literally grow perfect, flawless single crystals right in laboratories. We use these giant pressure cookers called autoclaves in a hydrothermal process. We've literally mastered the stone. So, that brings us to our final thought for this explainer. The next time you look at your smartphone, or check the time on your quartz watch, or even read the text on the screen you're looking at right now, will you remember the ancient, pulsing rock hidden inside? It's just a beautiful reminder that no matter how incredibly advanced our digital world becomes, we are still fundamentally relying on the remarkable physical properties of the Earth right beneath our feet. Thanks for hanging out with me for this explainer, and remember to keep questioning the technology around you.